It's August 1972, and Ian Richardson, a future NASA scientist, is watching TV when the BBC announces
the interference is caused by solar activity.
He didn't know it then, but the sun had just erupted in one of the most powerful solar events ever recorded. There was no threat to humans because Earth's magnetic field deflects much of the sun's radiation. But the explosions were so powerful that intense radiation disrupted TV signals and caused radio blackouts. So what if you were outside Earth's magnetic field? On the moon and beyond, astronauts face the risk of extreme radiation exposure. Luckily, the intense radiation in 1972 occurred right between the Apollo 16 and 17 missions, when no astronauts were in their path. As NASA plans missions to go back to the moon and then onto Mars, predicting the sun's activity to protect astronauts from space radiation is one of our biggest priorities.
One of the biggest unknown factors about going to space is the radiation hazard from the sun.
This is Ian today, studying the effects of the sun, also known as the field of heliophysics.
The sun is always emitting radiation like the light we see, but certain energetic particles, like from the August 1972 events, can be far more harmful.
To be able to forecast solar energetic particles, we need to know how the sun energizes them. The sun is made up of electrically charged particles called plasma. As this plasma moves, it builds up energy inside its massive magnetic field. This energy is usually released in two types of explosions. Flares are intense flashes of light. Coronal mass ejections are giant eruptions of solar material.
These solar eruptions send shock waves across the solar system, accelerating particles as they go.
These are solar energetic particles, or SEPs. They consist mainly of protons and possess a lot of energy that can affect satellite measurements and humans.
SEPs can bombard you with a lot of radiation in a short period of time. They can penetrate your skin, damage your DNA, and increase your chances of getting cancer and radiation sickness.
But they don't occur with every solar eruption. Only a small number of flares and coronal mass ejections create SEPs.
So we're trying to predict when SEPs form and how they travel through space.
At NASA's Goddard Space Flight Center, the Community Coordinated Modeling Center, or CCMC, is dedicated to testing prediction models. Working with global partners, they use data from NASA satellites at different vantage points and models to figure out how solar explosions behave, including how shockwaves energize SEPs. And as we get better at predicting, we get more time to prepare.
Preparation for an SEP event, of which you may know that is already coming and perhaps the magnitude as well, the technique that you would want to use is to put as much mass between you and the source.
On the surface of the moon or Mars, astronauts can go underground or build shelter with local materials. But in transit, astronauts can only be protected with what's on the spacecraft.
Which means that you might have elements on a spacecraft that have multiple purposes.
NASA's space radiation specialists are testing different ways to do this. One strategy they tested on the Orion spacecraft involves crew members barricading themselves with as much mass as possible in the center of the spacecraft. Other possible techniques in development include vests that add mass and electrically charged surfaces that deflect particles.
In terms of radiation protection and radiation mitigation, the factor of time is extraordinarily important.
The sun has a natural 11-year cycle that transitions through low and high activity, which is indicated by the number of sunspots on the surface. More sunspots mean more eruptions, resulting in a higher risk for SEPs. But during this increased solar activity, the sun's magnetic field strengthens, enhancing its shield against another important source of radiation, galactic cosmic rays. These are charged particles travelling at nearly the speed of light that are thought to come from supernova explosions from within our galaxy and possibly further out in the universe. If solar energetic particles are intense sporadic storms, then galactic cosmic rays are a constant drizzle. Galactic cosmic rays are more sparse, but also much more energetic. They include heavier elements that can penetrate through vast amounts of materials. Understanding the rate of galactic cosmic rays helps us determine how much time astronauts can spend in space safely. To date, humans have only been on the lunar surface for a cumulative total of about 12 days. A trip to Mars will take 6 to 10 months each way, That means even more radiation exposure, and so NASA is doing work to prepare for that.
The moon is going to be a test bed for us in order to be able to prepare for Mars. The more that we understand the impact and the duration of radiation on the moon, the more we can extrapolate that to the length of time that we will be spending in transit and on the surface of Mars.